Thank you very much, Javier. I almost was ashamed of how much he said. Well, first of all, I would like to thank you for two reasons. The first one is because you have given me that opportunity with this invitation for the presentation. I am very pleased to be here in Vigo. I have been already in several occasions, and always it's a pleasure to come back to this wonderful land and earth. Second, because I had the opportunity to present some of the recent studies that we are conducting in my research group, which is also the opportunity to try to connect the result that we have with another result from scientists around the world about what happens to our Earth at the present. Well, with this, I will go directly into the presentation. The title is The Global Change, What We Can Learn from Antarctic. If the global change is really existing, and what we can learn if it is true from that. Have already been presented by Javier, so I will not go into this with more detail. Or the presentation that we'll be doing from our data will be derived from what we have called the SCAN projects. These are projects that we have been conducting in Antarctica since the experiment was contracted in 1992. That was the first cruise of Antarctica, although in Antarctica of the experiment vessel. My presentation is with contribution from many other authors from Spain and from many other institutions around the world. Mostly we have in Spain the Geological Survey, the University of Vigo, we have University of Granada, people from the OGS, the British Antarctic Survey, so many other institutions which I will not go into the detail here. Well, there is a recent picture from the Earth, from the space of the Earth, and there are two points that I would like to stress here. The first of all is that we have 2 poles which are covered by ice, mostly covered by ice during most of the year. But these 2 poles are quite different. They are not similar in any aspect. The North Pole is characterized by sea ice which have an extension of about from 5 in summer to 15 in winter square kilometer. It's only a few meters thick, and most of this ice disappear during the summer. It's only 1/3 which remain covering the pole, the Arctic. In contrast, the South Pole, the Antarctica, is a continent. It's a rather large continent with very huge land masses. And these land masses are covered by a mean thickness of 2.5 kilometers of ice, and also the sea surrounding Antarctica. The sea have almost the same surface of ice during winter. Most of this ice disappear in the summer, which is our opposite summer. But during winter, the extension is about 14 million square kilometers, which multiply by 2 in winter. Well, now we are going to see a video, which I hope they will go to the end. You see, the Antarctica has 2 main parts. The eastern part is the continent, and the western part, the advantage of the going slowly, that we can see more thoroughly, is the western Antarctica, which is composed by islands and peninsula. It's not a real continuous continent, but since it is fully covered by ice, it's a continent, it's almost a continent, where you can go from one part to another without any problem. What is the importance of these 2 caps of ice in the Earth, in the north and in the south? Well, the most important effect that it has for the human being is that they control the present oceanic circulation, and also they control climatic circulation. So they actually controlling our climate. So the present thermohaline circulation is derived from the production of cold water in the pole, which moved southward and now northward, and they develop three larger components in the ocean, which are the present characteristic of the circulation in the ocean. The formation of this cold water only occur in very specific places. In the north, they occur in the Labrador Sea and the Greenland and Norwegian Sea. And in the south, they mostly occur in two seas, the Ross Sea and the Weddell Sea. The Weddell Sea is the most important one, since it probably produces about 80% of the total cold water which is produced in the South Pole, in Antarctica. The same for the atmospheric circulation. The production of cold air in the north and in the south produce convection cells, which move around the Earth, and they produce and they result in the present climate. But this feature, these characteristics, are not permanent in the Earth. They are rather recent features that have been developed in the Earth history at a very recent time. If we look into the result of the drilling for ice in the South Pole, the EPICA, which is the European project to drill the Dome Sea, and the Vostok, which was mostly an international effort by North America and many other nations, you can see the significant changes in temperature along the sea, the ice in the core. We have period like the present, which is interglacial and very warm in comparison to other periods which are cold. Even we had this one interglacial, there is another interglacial where the temperature was much higher than at the present. By the contrary, only about 10,000 years ago, which is a lot for human beings, but not a lot for the Earth. At this time, almost the Egyptians were already in existence, or the Egyptians were developing their own culture, the huge culture of the Egyptians. The Earth was about several degrees, probably 5 to 6 degrees below present temperature. As a result of this, the ice in the pole and the ice in lands, in the glacier inland, were largely developed. In this scene at the end, you can see the ice volume. Why these changes, these drastic changes in the temperature of the Earth? There are two forces which are controlling these changes. There are two main groups of forces. One of them is the external forces. The external forces, the most important one, are related to the changes in the orbit of the Earth, the inclination of the axis, the motion of rotation and precession, and the orbit around the Sun. But there are many other external forces which have changed drastically the system in the Earth. These are the solar activity variation, which are very well known, and they have a cycle, and they have changed drastically along the time of the Earth's existence. The meteoric impact, like the extinction of the dinosaur at the end of the Cretaceous, because a large meteorite was impact in Mexico. And more recently, also external forces, which are induced by the human activities, and these are the industrial activities. All these are external forces. But there are also internal forces which change the behavior of the Earth and the system, how is operating the system Earth. And these include plate tectonic, the motion of the continents in the surface of the Earth or in the crust of the Earth, the creation of new seaways which connect different oceans, and they create passage where the water masses may interact and be interchanges. The variation in sea level as a result of the concentration of ice in land, because the concentration of ice in the sea does not change sea level. And finally, the thermohaline circulation. So drastic changes have been occurring in the history of the Earth as a result of this factor. One of the major changes occurred during the transition of the Eocene-Oligocene, the most recent change. The Cretaceous was also a very drastic change in the Earth, but that was because the standard forces created by the impact of the meteorite. But the transition, where we were concentrating in the stock between the Eocene and the Oligocene, at this time, 33 million years, was a drastic change in the temperature of the Earth, which implied at that moment the beginning of ice in Antarctica. And that would imply also the change from a 2-layer circulation in the ocean to a 3-layer circulation in the ocean because of the creation of the thermohaline circulation. Most recently, when we have instruments that we have been able to measure the change in temperature, we have observed, again, a drastic change in the temperature of the Earth. This drastic change has been accelerating during the last century, and that coincides with the large development of the industry. And that would have been called the temperature change. Temperature change, where everyone knows and we are concerned about what it happens. Why this change? Well, if you look at this illustration, it's very easy. It's very easy why that has changed. If we look in the total population, that the OECD population, which has had an increase of about 10% since 1980 to 2020, which is prediction, it's only 10% increase, but if we look into non-OECD country, we have an increase of population of about 40%. So we go from about 3.5 million people on the Earth to more than 6 million people on the Earth. And these people need food, need to be heated, need to go to the school, they need to go to the cinema, and that produces a lot of gases. Gases that have what is called the greenhouse effect. When you put in the atmosphere gases which prevent the reflection to the atmosphere of the radiation from the sun, this radiation come back to the Earth, they produce the greenhouse effect, like what you produce when you have a greenhouse in your house, and then increase the temperature of the Earth. So what we see with the instrumental data, we have an exponential increase of these gases with greenhouse effect since 1750, and mostly during the last few decades. So these are the diagram where you see these drastic changes, which are exponential in several orders of magnitude. However, gases with greenhouse effect have also changed in a natural way before the humans were in land, on Earth, before. So when the study of these gases in the core for ice, they show significant changes in this concentration in a cyclic manner, very similar to the temperature. This one is not, but the CO2 is very much related. Also, again, a drastic increase, which is not similar to the increases that we can see for the last 100,000 years, for the last few 100,000 years. It's only during the last century when we had the drastic change in these gases with greenhouse effect. However, as I said, these changes have occurred always along life in Earth. What are the basic aspects associated to the change that we observe? Well, what we observe is not only a change in temperature. We observe a global change which implies many more things than only the change in temperature. The global change implies changes in the atmosphere and the ocean, changes in the pattern of the thermohaline circulation on the climatic zones. Temperature increase is one of the effects. It's the more obvious one. It's the one that we see, because now we are here in January at the end of May, and probably before you have something more than this. Loss of cryosphere, losses, significant losses of ice, not only in the pole, but also in the land, in the continent. Sea level rise. Now, later we will see why the sea level rise and who produced the sea level rise. Increases in land erosion in the area where they are suffering from desertification. These areas are really being eroded. Loss of land masses because the increase in sea level. And reduction of terrestrial and aquatic ecosystem. We are observing an increased losing in the eco-diversity because many of the species are disappearing. And finally, changes in agriculture and fisheries. So the global change is not only the change in temperature, it's many, many more other effects that are affecting the evolution and the functioning of the Earth system. Let's go now and see how it has been evolved, the distribution of ice in the two poles, in the north and in the south. As you remember, the north has no lands, it's just one ocean, the Northern Ocean with many seas around. Well, in here, what we have observed, average ice thickness decreased by 40% during the recent year. So it's almost half of what used to be had disappeared because of the increase in temperature. If we go to the Antarctic, we observe just the opposite, which is intriguing. Why we are decreasing the thickness and the distribution of ice in the north, and we are increasing that in the south? So what we see is an increase of about 10% in the last 30 years of ice, the sea ice in the Antarctica. What happened with the ice in the continents? Also the same. One increase of the ice in the continent in Antarctica in comparison to what happens in the North Pole. Why this difference between Antarctic and Arctic? Well, there are several basic reasons that you may already be thinking of. It's partly due to the very little warming that is observed in Antarctica. Antarctica is an isolated continent. It has a thermal isolation produced by one oceanographic current. They move around the continent in the same sense of the wash to the right. That is the Antarctic circumpolar current, which produces a thermal isolation of the continent. So this is according to the SCAR report. Also, the ozone hole in Antarctica produces an isolation of the Antarctic continent. The ozone hole is expected to be being reduced in the next few decades. If that happens, then the Antarctica will lose this part of the isolation due to the atmospheric circulation. So it will experience at least partially a loss of ice in the sea. Now we know also the increase of sea level rise. From where it comes, this increase in sea level rise? Well, you may think, since the ice is lost in the Arctic, that will produce increase on sea ice. No. because the volume which displaces the ice in the water, once it melts, reduces its volume, and there is no increase in the level. It stays the same. Doesn't matter it's how much ice you put in the ice, in the water of the sea, or well, the volume, the sea level will be exactly the same. So the only source from ice to increase sea level comes from the continents, from the ice which is stored in the continent. The sea level, mean increase in sea level during the last few decades is about 1.7 millimeter per year, which you say, well, 1.7 millimeter is nothing, something like that. But if you multiply that by 1 century, and we see later what are the predictions, can be significant. Where can be significant? Can be significant in lowlands, like deltas, estuaries, marshes, and you have to take into account the largest concentration of population occur now in lowland area, like Bangladesh. Bangladesh will disappear with a couple of meters of sea level rise. And there are also countries in Europe, like Netherlands, which are below sea level. They are protected from the sea by walls. But also area in Spain, like the Ebro Delta, the Guadalquivir marshes, Doñana, all this area will disappear with an increase in a few decimeters of sea level rise. Where it comes? Well, the most important contribution of sea level rise comes from the thermal expansion of the sea. It's not from the melting of ice in the continent. The melting of ice, Antarctica ice sheets, is only contributing about 0.24 millimeter per year to that increase. Expansion of the sea, 0.75. But there is another very important component of this increase in sea level rise, and is that the glacier and ice caps in the continent, mostly in mid-latitude continent, not in the Antarctica, which is not losing ice, mostly in Europe, in Southern America, in all these places where we are experiencing the largest loss of ice and increase in sea level rise. So during this presentation, I will focus in aspect of the geodynamic and paleoceanographic evolution of the oceans in Western Antarctica. For that aspect that I will be discussing, I will be based in geophysical data and seabed sample they have been obtaining during oceanographic cruises in the Antarctica. And the final objective of the presentation will be to assess what can we learn from the Antarctic evolution in order to predict the Earth evolution in the future. I don't know if I will be able to do that, but at least I will give you some hints so you may think about and investigate and go beyond what we have done so far. You are the future, the young people. So let's talk initially about the tectonic evolution of Antarctica. That is a reconstruction of 70 million years ago. So the Antarctica was a continent attached to South America on one end and to Australia, New Zealand, and Madagascar on the other end. So it was a continent without ocean around. It was a continent not really isolated. At 30 million years ago, the continent, because plate tectonic, have already separated. One land have break up, and you have a continent in the South Pole. Since that moment already, at least very little after the Cretaceous, you have the continent in the South Pole, but already isolated from South America, from Australia, New Zealand, and Madagascar. What is happening because of that? the creation of new seaway allow the installation of a circumpolar current called the Antarctic circumpolar current. And what produced that circumpolar current? Produced the thermal isolation of the continent. The continent, for the first time, became isolated from the rest of the continents and in a polar position. What will result from that? The creation of sea ice, or ice. Then in the Miocene, already the continent is very well established. In its present position, seaway have already been created, new seaway, and a very active circulation, paleoceanographic circulation result, not that only from the circum-Antarctical polar current, but also by the creation of cold water in the Weather Sea and the Ross Sea, which circulate to the north and influence and control the thermohaline circulation. Since the importance of these seaways during the International Polar Year 2007-2008, it was created a project to investigate the development of the stray and the influence of this stray in the present global system. So that was the Plate and Gate project, and we have analyzed, we particularly were involved in the study of the Drake Passage, but other people were involved in the study of the South Tasman Rise stray that was created slightly earlier than the Drake Passage, and also some people were investigating the important strait and seaways in the north and the mid-latitude. Why is this important? Why should we spend money? In this moment, we have no money. The country has no money, nowhere is money, everything is in the bank. Well, it's spent by the banks. Why we should spend money in investigating the Antarctica? Well, the investigation on Antarctica have allowed us to analyze the creation of the present circulation system. And the present circulation system controls climate. And where we live? We live in this Earth, where the climate is one of the most important factors which is influencing our lives. So that's important to know how the seaway have been created and how circulation have been affected. For the same reason, not only the ACC was important, also the creation of cold water in the pole, and particularly in the Antarctica, is important because the weather gyro produces about 80% of the cold water from the South Pole that is circulated in the present oceans. And finally, we have a question. Who was first? The creation of the seaways and the circulation, the isolation of the system, or just the contrary? Because the system was isolated, you create the ice caps and you influence later on the circulation. Well, that is the question that I will be addressing during my presentation. I hope that you can give me more answers than I have now, because I still have a lot of questions. These are the cruises that we have been conducting in Antarctica with the VS Parides in 1992, and these are some of the track line that we have obtained during these cruises, and we will see some of the data. We will see some of the data that we have obtained. We have been using basically geophysical method. We have done also sampling, but only very recently. Until now, we have been involved mostly in knowing the nature, the structure, and the characteristic of the sea floor and the sediment and the rock below the sea floor. The geophysical method includes the swath bathymetry. Some of you already may have participated in oceanographic cruises that produce the relief of the bottom, like if you were taking a photograph of the Earth from a satellite. So you have a map like that. Here this is about 50 kilometers, probably 60 kilometers, and 40 kilometers in distance. So So you see the detail that we can observe the relief of the sea bottom. We also obtain with high resolution size system what is the sedimentary cover and the nature of that sea bottom in a few with a thickness of several meters, but very, very high resolution, a lot of detail. But also we use method that allows us to go deep in the earth to at least to the Mohorovic discontinuity. That means the crust. We observe the oceanic crust in the composition of the oceanic crust and all the rocks and sediment that we can obtain there. In order to see that, we have what we call air guns, which are the instrument here. They accumulate air at very high pressure. It is released in the water column, produce an implosion, and this implosion produces waves, seismic waves. They go to the bottom of the sea and they are reflected back to the surface, and using these waves we can analyze what is the nature and composition of the bottom. To record the waves that we are producing with the guns, we have what is called the streamer, which is this drum here. It contains sensor, and they have a length of about 2.5 kilometers, and this trail behind the vessel, and that is the one that is recording the wave, the seismic signal that is reflected from the sea bottom. Here is the operation. So we have that is the guns when they have no impact in ecological impact. Many studies have been done on this respect, but some people are still concerned about the problem, but really many studies have been done. Anyway, we are very concerned when we are deploying the guns, and we look for waves and things like that in order not to have any operation when the waves are close to the vessel. And that is the kind of result that we have. Here we have the depth in seconds, and you can extrapolate that from the bottom. Here, the bottom of the sea is a 4 seconds to two-way travel time, so it's 3,000 meters, roughly 3,000 meters, and that the sediment in here have a thickness of 2 seconds, about 3 kilometers of sediment. Below that, we also have data, and we go to the Mohorovic discontinuity, which is about 8 kilometers deep. Also, we obtain gravimetric studies. We obtain the gravimetric anomalies that are in the sea, and also the magnetic anomaly. We record the magnetic anomaly in order to assess expansion of the ocean and the nature of the crust below the vessel. And finally, we obtain sample. We look for where we can we have sample from the rocks or the outcroppings or the Indo-Oceanic crust. See if you these are a large chunk of Indo crust or the basalt. And also we do sampling, and we obtain sediments in order to analyze the detail of the paleoclimatic or paleoceanography and sedimentological evolution of the sea bottom. This slide was prepared by Javier Hernandez. It's very detailed, very complicated. I will summarize that. But we can see in here two main flows. The circumpolar current, which move toward the east, and the weather gyro, which produces a gyro in the weather sea, and from which are derived several bottom flows that move northward. Simplifying that in this slide, which is much easier, that's mine. We have the Antarctic circumpolar current, which moves across the Drake Passage into the Scotia Sea, back to the north into the Atlantic Ocean, through the North Scotia Ridge, and into the Atlantic Ocean, back to the east, and then to the south and the west. And the weather gyro, which produce bottom current, the weather sea bottom water, which move into main branches. One of them moves northward into the South Scotia Ridge. They go into Power Basin, and they go into the Scotia Sea through passages in here, and also through James Basin, they go into through the Scotia Ridge, into the Scotia Sea, and back into the Pacific Ocean. And then there is another main branch which goes northward in front of the South Sandwich Trench and into the Atlantic Ocean to produce the cold water of the Atlantic Ocean. That's the Antarctic Circumpolar Current and the Weather Sea bottom water. So there's the deep water which is moving to the Pacific. So if we look into there is a satellite gravity and anomaly map of the Drake Passage between South America and the Antarctic Peninsula, and here what I like to stress is the presence of front, which are, that one is the polar front. These front are related to the main water masses that are flowing in this region. These front go to the surface, from the surface to the bottom of the sea. They are inclined surface and they move huge water masses. They are important for the circulation and the climate. How is the situation? How we can learn from the past to the present? Well, in this slide, which is summarized by Miller and colleague in 2008, there are two main graphs. One of the graphs is the sea level, the temperature of the ocean based in the isotope, a stable isotope of the foraminifera, and the other curve is the sea level changes, which have been derived from analysis of the continental margins, and also from analysis of the isotope in cold. So what we see is that there are taken into consideration this temperature and sea level curve, that there were times through the history of the Mesozoic to the present history where possibly small ice caps were developed in Antarctica, taking only in consideration this fact, temperature and sea level rise, sea level changes. But also it's important to notice that there is a very significant change in the transition from Eocene to Oligocene. It's the most drastic changes in temperature and also the most drastic change in sea level. Why this? Where were the forces which are produced, that have caused this evolution of the Earth? We have no data to say that that is an external force, like a meteorite. So it has to be something probably internal in the Earth, which induce this phenomenon. So summarizing the previous slide, we can say that ephemeral ice sheets may have existed in Antarctica from late Cretaceous to Eocene. The major global deep sea isotope record shift occurred in the Eocene-Oligocene transition about 33.5 million years ago. And then the question is, who is the driver of these changes? Because the ice, because the climate, because change in the Earth, and that is the question. Well, let's go back and see some more of our data. That is the tectonic setting of the Scotia Sea. The Scotia Sea shows a mosaic of expansion ridges, flow line, magnetic anomaly, which allow, using geophysical method to reconstruct the evolution of this sea. The tectonic setting so resorted because the separation of South America and the Antarctic Peninsula result the Scotia Sea, which is composed at present by two major plates. One is the Scotia plate to the west, and then another one, the Sandwich plate to the east, which are separate, but it's spreading ridge. In this spreading ridge, new oceanic crust is produced, and as a result of that, this Sandwich plate and the whole Scotia Sea is migrating into the Atlantic Ocean above the South American plate and the Antarctic plate. So now we will see the tectonic reconstruction of the evolution of Antarctica since the Mesozoic. So here we still have a single continent, 70 million years ago, 60 million years ago, still a single continent. 34 million years ago, we already have separate. The Scotia Sea is developing. The fragmentation of Gondwana produced all these fragment of continental crust which is spread around the Scotia Sea and produce the separation of the South America and Antarctica. And we go back to the end, to the present situation. Current debate. There are two major proposals for the cause and forcing of this phenomena of the creation of the present climate. One of these proposals is tectonic, because we have internal forces, the one which produce new seaway, the separation of continents, the breakup of Gondwana, which produce shallow ocean gateway, which allow the isolation of the Antarctic continent. The second hypothesis is that it's not because of that, it's because in the climate we change something. The climate we change the concentration of the gases with greenhouse effect, precisely the CO2. And this one is responsible for the isolation of the Antarctic and the production of the ice cap in the continent. So we will see now some of this hypothesis. The first one was produced forward in 1977 by Kearney, but the main inconvenience of the hypothesis is that there were no data to prove that the opening of dry passage occurred in coincidence or before or deterioration of the climate to low temperature. Later studied, they get closer, and even there is a hypothesis, but not real data, they propose that probably the passage was already in existence by the Middle Eocene. The second group of hypotheses are climate. So the one which produces atmosphere, and another using climate also show the importance of the opening of the type passage in this climatic influence for the evolution of the present climate. Let's go back to the tectonic. So we see again the reconstruction 50 million years ago. So in the hypothesis, which was actually the most accepted one until a few 10 years ago roughly, they do not open the dry passage until about 30 million years ago. So the tectonic hypothesis had the problem for the influence on climate is the opening of sea or the seaway of the dry passage later than the climate deterioration. So what they do, the proposal of the quantum is that drastic changes in CO2 concentration are the cause for the deterioration of the climate and in consequence of the development of the sea sheet, or the ice sheet in Antarctica. So in here in this diagram, you see with concentration of CO2 similar to the present one, in the level of 280 ppm, you have the concentration of similar ice cap, smaller but similar because they run this program only for 10,000 years. They have an integration 10,000, similar to the present. But when you have 8 times the concentration of CO2, they no ice. No, that's just deposit. A lot, no ice. They claim that the opening of their passage was not significant. They claim in terms of the paper. But themselves, they produced several models with several concentrations of CO2, and particularly in the model where they used 2.85 ppm per the CO2, the opening of dry passage is very significant for the temperature and the development of sea ice. So even themselves, although they said that that's not important, probably based on this diagram, in these two diagrams, they claim the opening of dry passage was not important. Another author, well, that is important. You see, this is the model at 2.4 per ppm CO2. How here at the bottom you have in 1,000 years how the ice are developed with this concentration of sea ice in this concentration of CO2 in the atmosphere. Another author, in this case, Silk and England, another colleague, they have produced also models of the sea ice distribution, opening and closing dry passage, and also change the concentration of CO2 in the atmosphere. So the model that they produce, they all show a drastic change in the temperature of the sea, whether the dry passage is open or closed. So these are the several models with this sea dry passage open. They have several runs. These runs are with several concentration atmospheric CO2. Atmospheric CO2 multiply, I don't see that, it multiply. So you see how different is the concentration of sea ice and the temperature of the sea, depending whether dry passage is open or closed. So that is a summary also of the dry passage campaign. You see the relief at the bottom. Here is concentrate is our result, but the result of British Antarctic Survey compiled on the graph. The satellite anomaly map, gravity anomaly map of the Scotia Sea also show these features: significant development or spreading center, flow lines, and the spreading ridges. The present one in the eastern Scotia Sea, the South Shetland Trench, where the subduction occurred of the Atlantic plate below the Scotia plate. The map with the seismicity also show the distribution of the main earthquake in this region, and they all concentrate in two major areas, which is the boundaries of the Scotia plate, the northern Scotia Ridge and the south Scotia Ridge, and also in the spreading center, and also in the subduction zone. So this is a very, very active zone, and this seismicity reflects the development of new oceanic crust and the expansion of the Scotia Sea into the Atlantic Ocean expansion that we will see now from when that happened. That is the detail of the end of the Shackleton fracture zone into the Scotia Ridge. The relief, and in that relief I show this feature because there is a very important feature in the dry passage, which have been claimed to be one of the major barriers to the circumantarctic flow, and this is the Shackleton fracture zone. This relief, they have almost 3 kilometer relief above the median depth of the sea floor. Here is again the same Shackleton fracture zone, the relief obtained with the SINRAD swath bathymetry in one of the Sperry screws, and the tectonic of this region with the intersection of the South Scotia, of the Shackleton fracture zone below the Scotia, the Scotia arc. Here is the 3D representation of this area. So we have mostly subduction in the South Shetland Trench, partly subduction below the South Scotia Ridge, and the subduction of the Antarctic of the Shackleton fracture zone below this piece of continental crust. When that occurs, when the tectonic begin to be active in the Scotia region, because we have here the main problem of knowing whether the Drake Passage was important or not in order to influence present climate. This is a compilation of the most available magnetic anomaly and the oldest magnetic anomaly that was recognized in the Scotia Sea was magnetic anomaly 10, which is about 28 million years ago. So with this compilation, it was not possible to confirm the Drake Passage was open before or at the age of the climatic change. There is the region, the reconstruction for 32 million years ago. So really, no Drake Passage, no Drake Passage before 32 million years ago. We have obtained a magnetic profile, the profile Drake 17, where we have been able to recognize magnetic anomaly 12. There's one here. This magnetic anomaly is 32 million years old. So we have here the profile, or another profile, the 5, with the magnetic anomaly that we are recognizing. Here we have magnetic anomaly 12. So if we take into consideration the extension of the continental crust and the expansion of the oceans, we reach the oldest oceanic crust that we have dated in the Drake Passage is 33.3 million years old. That coincides exactly with the timing of the major deterioration of the climate according to the oxygen isotope of the foraminifera. What does this mean? The first time we have been able to prove the Drake Passage was already at oceanic depth at that time, my first time. But if we take into consideration the timing for breakup of the continent, you not produce ocean at once, you have to have a timing for breaking. And that timing for breaking has been calculated with the studies that we know in the different oceans about at least 5 million years. So it means that by 5 million years before 33 million years, we already have seaways, shallow seaways, connecting the Pacific and the Atlantic. And these shallow seaways have allowed a proto-Antarctic circumpolar current. The full opening of the strait by 33 million years ago produced the total isolation of the Antarctica and produced the drastic or induced or favored the large decrease in temperature of the Earth. That is the profile that we see, and the importance then is to see here that we have many deposits, a very thick sequence of deposits, and on top of the oceanic crust, which in addition to that have been subducted, partially subducted below the Scotia arc. So we have the dynamic summary. We can say that the seafloor dry passage reveal a hot or flow lines, spreading center, and magnetic anomalies, which facilitate the reconstruction of the processes of fragmentation of South America and Antarctica. New result of the structural and magnetic anomaly of dry passage confirm the opening of the seaway prior to the Eocene-Oligocene boundary. That means more than 35 million years ago. Finally, the seaway allowed the instauration of the Antarctic circumpolar current as a consequence, the thermal isolation of Antarctica. Now we go in another aspect of the study that we have been conducting in Antarctica, is what we can learn from the deposit. And here we were interested until now mostly in the dynamic, in the structural, and in the nature of the crust, oceanic crust. And here now we are going to be knowing a little bit more because of the knowledge that we can derive from the deposit. So we will be analyzing seismic stratigraphy and bottom current, the age of the deposit. We will do an assessment. Unfortunately, we do not have ocean drilling program exactly in this region. We have nearby, but not in the region. We will make an estimation of the order unit that will discuss tectonic and global events. Again, that is the source bathymetry of the Central Scotia Sea. And only just looking into this bathymetry of the sea floor, we can observe a myriad of relief, erosional feature, and relief which reflect active bottom current, very active bottom current, which imply that they are deposits which are being eroded and deposits which have been deposited, that's an area where deposits have been formed. So that is again a compilation by Javier of this region, the same region. Here is the present bottom relief, here the interpretation, and from that we have been able to recognize two main groups of deposits which are derived from the weather flows, and these are concentrated in the south, and we have contour wave, drift, every type of deposit that you can imagine. That is an area to develop a book in bottom features. And deposits which are associated to the Antarctic circumpolar current. And again, there is a huge amount of deposit, elongate, mount, drift, and many other sediment wave, or every type of deposit. The stratigraphic unit, we have been analyzing all the seismic stratigraphy of the region, and we have been able to define the main seismic unit that can be recognized in the area. These units are separated by horizons. They have a very characteristic seismic signature that can be recognized regionally. And because of that, we believe that the horizon represents significant changes, paleoceanographic changes, in the regime of the bottom water circulation and the flows. So that is the thing that we are going to see briefly. So mostly, there is a very important reflector, which is called reflector C. That reflector C implies a major paleoenvironmental change in the whole basin. And we believe that is because that reflector C has recorded the major change in the paleoceanographic circulation of the region. Here is another reflector that we observe. And here you see that is reflector C, that one. And how we date this reflector? The thing that we do normally, we do many different approaches. One of the most typical that we do, we know the age of the oceanic crust in here because they have magnetic anomaly. We have the magnetic anomaly, knowing how if the age of this oceanic crust here is 13 million years ago, or accumulate is about that one is younger than that. That one is about 12 million years ago. So we have in here one reflector that is on top of that unit. It appears beyond that unit. So we know that that reflector has to be at least as old as the oceanic crust below, or probably younger. So on that basis, we have in here a maximum age for that reflector. Has to be younger than 12 million years ago. Doing that in different regions, we have assessed the possible age of the reflector. Another approach that we use, using sedimentation rate and thickness of the deposit about the oceanic crust. We compare this sediment with the result of the ocean drilling program in James Basin. It's in the region, it's not exactly in the Scotia Sea, but it's in the region. And from that, we know the age of the seismic unit, extrapolating sedimentation rate and the age of the crust below. We come to assess roughly a boundary condition for the ages of the different reflectors. The southern Scotia Sea terrorized shows the ordered deposit of the region. And this deposit, we have been able to assign to them an age that is from latest Eocene to early Oligocene. And so that this deposit record the initial stages of the opening and creation of the Scotia Sea. So that is the reconstruction using this data of the circulation patterns at 21 million years ago. The only flows that we were able to recognize in the Scotia Sea were derived from the Antarctic circumpolar current. This flow came into the Scotia Sea, into the different basins, and they circulate eastward and later northward through the passage of the Scotia Ridge into the Scotia Arc into the Atlantic Ocean. All the flows from the weather gyro only move into the Pacific Ocean, like that. What happened in the middle Miocene from about 13 million years ago? We have, because of plate tectonic and the creation of new weights and seaway, James Basin opens its connection to the Scotia 3 through a passage in the South Scotia Ridge. So, at that moment, flows from the Weddell Sea were allowed to come into the Scotia Sea and move northward and westward to the Pacific Ocean. This flow then create a new paleoceanographic setting in the Scotia Sea, and the reflector sea has recorded this event. Then if we look, then here is our reflector. Again, we have the oxygen isotope, the compilation of the major event in the creation of ice sheet in Antarctica. Western Antarctic ice sheet developed at this moment, Eastern Antarctic ice sheet developed at this moment, mid-Miocene climatic optimum, and the reflector sea. So that reflector sea really coincides with a decrease in the oxygen isotope, that means a decrease in temperature, and also a decrease in sea level, and also coincide with the opening of the James Basin. Reflector B coincides again with another shift in both the oxygen isotope and the eustatic curve, and also coincide with the end of spreading in the West Scotia Ridge. And reflector A is another reflector. They also coincide with the with a larger shift in the deep oxygen isotope record, the isotope curve, and the development in the northern hemisphere of the ice sheet. The past and the present. Here is the past, the isotope curve. They show all these significant changes from interglacial at the present with major ones, interglacial to glacial. The last glaciation in Antarctica is an idealized drawing, and the present situation. What are the main conclusions that we have from the presentation so far? From the tectonic point of view, oceanic spreading at Drake Passage was active since 33.3 million years ago. But shallow gateway existed much before, probably before 40 million years ago. We have identified 6 main units, seismic units, 5 reflectors, all of them reflect or record major oceanographic change. The regional unconformity record intensified bottom current and may be correlated with the dynamic of Antarctic ice sheets, the deep water production, and hence wet climate. So the final conclusion is that early gateway at Drake Passage, prior to the Eocene-Oligocene boundary, combined with a CO2 decline and orbital forces, are probably the driving mechanism for major paleoceanographic and climate changes at the present ice world. If we look again, the past and the future, the past in this representation is here, from present 0 million years to 80 million years ago. That is the climatic curve with the major event that have occurred from the ecological and paleoenvironmental point of view in the Earth. For example, the extinction of the dinosaurs with a standard force, meteorite. But Antarctica is a drastic change in temperature in the Eocene-Oligocene boundary, major glaciation, persistent Antarctic ice sheet develops, and the northern hemisphere ice sheet begins. The future, using the present increase in global temperature, we can extrapolate with 2 scenarios, the IPCC scenario. One of them is the coolest scenario, and then the other is the warmest scenario. So if we extrapolate that, in that one, the scale is very different. In here we have million years, above that we have hundreds of years, from 0 to 500 years. So if we take 100 years, we go to this point when persistent ice sheets begin to develop in Antarctica. That means that we will decrease significantly the amount of ice in Antarctica. But if we take 300 years and go back to here, we get to the time of the extinction of the dinosaur. I hope that is not going to happen. So what will happen with the sea level? Again, we have a scenario where with high sensitivity, the highest sensitivity and the lowest sensitivity. And we have the model. So if we will go back, for example, to the end of the century, in this scenario with the world, we have an increase of sea level of about 0.8 meters, a lot. The Ebro Delta disappeared, the Guadalquivir marshes disappeared, or the lowland disappeared. Well, we have to consider several aspects about the global warming and the dynamic of the Antarctic. The first is that in Antarctica we will not expect significant changes in the short term. Why not? Because Antarctica is isolated by the ocean and by the air. So the changes will be minor. I haven't put that into here, but also if we increase temperature and we increase evaporation rate, more rainfall will develop. More humidity in the atmosphere, more rainfall. In the dinosaur time, the temperature was 5 or 6 degrees higher than now. There were huge forests all over the earth, and that's because there was a lot of rain. So increasing temperature, at the beginning you produce desertification in some area. But in the long term, you will produce a lot of water, expansion of the ocean, more lowlands, and more humidity in the earth. The Antarctica is a desert. The rainfall or the snowfall is very, very minor. It's very little. If you produce more air, more ice, more rainfall, at the beginning it will be just the opposite. More ice in Antarctica. So in the short term, one effect will compensate the other in Antarctica. So the Antarctica sheet will remain. It has been there for more than 30 million years. We are not so strong to destroy that in a few decades. We may, but no, not shortly. Again, contribution of Antarctica to sea level rise, minor. The contribution to sea level rise is coming from glacier inland, in the mountains, and a small ice cap, but not from Antarctica. But development of ice cap and to be destroyed, that depends on thresholds. And the thresholds are very sensitive. So once you reach a point, there is no coming back. Like this door, when you go in, then you cannot come back. Like in the airport, you go back, forward, you cannot come back. And here we happen the same in the Earth. Once we go beyond the threshold, the door, we will not come back. Finish. The Arctic, in contrast, is very sensitive. The Arctic may disappear if the present trend of global warming will continue. Some people are very happy. They will say, oh, we will open new navigation line. We will open navigation through the Arctic. We will go very far from North America into Europe. Yeah? You destroy a lot of things. So, another aspect, what we can contribute in science to global change. I think it's a future. The global change is beyond the climatic change, and it has been operating through the Earth's history. It's nothing new. It has always been there. Again, the global evolution is characterized by thresholds, which can be overpassed, and if that happens, major changes will occur, drastic changes. Human activity, we are small, but we may trigger that. The Earth system is rather independent. It's much beyond what we can do. We can see what happened with one small earthquake or one tsunami. We have a lot of technology, but we are small. We're very tiny. So the Earth is rather independent. But the Earth is sensitive to what we do. At the present, the final is that it's not working the Earth as an analog system. It's changing. It's not working in the analog system like the past. The future may not be like the past. Learning from the Antarctic. So that was my question at the beginning. Why we should go to the Antarctica? It's expensive. We need vessels, we need very nice clothes, which are expensive too. Not because they are nice, because they are very good, very warm. We have to go a lot of people, and that costs money. We have seen that the Antarctica is like a book. We have many different processes that we can study and analyze in order to understand science. And Antarctica is that, a place to analyze science. The development of seaways in Antarctica was a major, or is a major component of the basic climate system, circulation and weather. The Antarctic system is exceptionally dynamic. It's very sensitive. It's stable because it's self-independent. So far it's self-independent, but may not be. And we are responsible for the preservation. There is a protocol. But what happens if the population keep increasing? We are 6.5 billion people on Earth. Only that has doubled in the last 30 years. What happens if we go to 15 billion people on Earth? The resources will be searched everywhere. There will be no sanctuary. Every place they have a resource will be taken. Finally, the Antarctic is a natural laboratory from which we can learn about the behavior of the Earth system and help to predict the future evolution. Two actions to be promoted. An ethic for the strategy of use and control of the Earth in order to preserve the global system. And finally, active promotion by the government and the society in general. Finally, the politicians sometimes listen to the society. In many cases, not most of the case. In some cases, yes. In a new emerging global science oriented to the better understanding of how the Earth naturally operates and reacts to external forcing in order to assess the controlling factor. Science, hope for science. And finally, we are being observed about what we do with our planet, and for the moment, only planet. Thank you very much, Javier. I almost was ashamed of how much he said. Well, first of all, I would like to thank you for two reasons. The first one is because you have given me that opportunity with this invitation for the presentation. I am very pleased to be here in Vigo. I have been already in several occasions, and always it's a pleasure to come back to this wonderful land and Earth. Second, because I had the opportunity to present some of the recent studies that we are conducting in my research group, which is also the opportunity to try to connect the result that we have with another result from scientists around the world about what happens to our Earth at the present. Well, with this, I will go directly into the presentation. The title is The Global Change, What We Can Learn from Antarctic. The global change is really existing, and what we can learn if it is true from that. Have already been presented by Javier, so I will not go into this with more detail. Or the presentation that we'll be doing from our data will be derived from what we have called the SCAN projects. These are projects that we have been conducting in Antarctica since the experiment was contracted in 1992. That was the first cruise of Antarctica, although in Antarctica of the experiment vessel. My presentation is with contribution from many other authors from Spain and from many other institutions around the world. Mostly we have in Spain the Geological Survey, the University of Vigo, we have University of Granada, people from the OGS, the British Antarctic Survey, so many other institutions which I will not go into the detail here. Well, there is a recent pitching for ice in the South Pole, the EPICA, which is the European project to drill the Dome Sea, and the Vostok, which was mostly an international effort by North America and many other nations. You can see the significant changes in temperature along the sea, the ice in the core. We have period like the present, which is interglacial and very warm in comparison to other periods which are cold. Even we had this one interglacial, there are another interglacial where the temperature was much higher than at the present. By the contrary, only about 10,000 years ago, which is a lot for human beings, but not a lot for the Earth. At this time, almost the Egyptians were already in existence, or the Egyptians were developing their own culture, the huge culture of the Egyptians. The Earth was about several degrees, probably 5 to 6 degrees below present temperature. As a result of this, the ice in the pole and the ice in lands, in the glacier inland, were largely developed. In this scene at the end, you can see the ice volume. Why these changes, these drastic changes in the temperature of the Earth? There are two forces which are controlling these changes. There are two main groups of forces. One of them is the external forces. The external forces, the most important one, are related to the changes in the orbit of the Earth, the inclination of the axis, the motion of rotation and precession, and the orbit around the Sun. But there are many other external forces which have changed drastically the system in the Earth. These are the solar activity variation, which are very well known, and they have a cycle, and they have changed drastically along the time of the Earth's existence. The meteorite impact, like the extinction of the dinosaur at the end of the Cretaceous, because a large meteorite was impact in Mexico. And more recently, also external forces, which are induced by the human activities, and these are the industrial activities. All these are external forces. But there are also internal forces which change the behavior of the Earth and the system, how it's operating the system Earth. And these include plate tectonic, the motion of the continents in the surface of the Earth or in the crust of the Earth, the creation of new seaways which connect different oceans, and they create passage where the water masses may interact and be interchanges. The variation in sea level are a result of the concentration of ice in land, because the concentration of ice in the sea does not change sea level. And finally, the thermohaline circulation. So drastic changes have been occurring in the history of the Earth as a result of all these factors. One of the major changes occurred during the transition of the Eocene-Oligocene, the most recent change. The Cretaceous was also a very drastic change in the Earth, but that was because the external forces created by the impact of the meteorite. But the transition, where we were concentrating in the stock between the Eocene and the Oligocene, at this time, 33 million years, was a drastic change in from the Earth from the space of the Earth. And there are two points that I would like to stress here. The first of all is that we have two poles which are covered by ice, mostly covered by ice during most of the year. But these two poles are quite different. They are not similar in any aspect. The North Pole is characterized by sea ice which have an extension of about from 5 in summer to 15 in winter square kilometer. It's only a few meters thick, and most of this ice disappear during the summer. It's only 1/3 which remain covering the pole, the Arctic. In contrast, the South Pole, the Antarctica, is a continent. It's a rather large continent with very huge land masses. And these land masses are covered by a mean thickness of 2.5 kilometers of ice, and also the sea surrounding Antarctica. The sea have almost the same surface of ice during winter. Most of this ice disappear in the summer, which is our opposite summer. But during winter, the extension is about 14 million square kilometers, which multiply by 2 in winter. Well, now we are going to see a video, which I hope they will go to the end. You see, the Antarctica has two main parts. The eastern part is the continent, and the western part, the advantage of the in slowly that we can see more thoroughly, is the western Antarctica, which is composed by islands and peninsula. It's not a real continuous continent, but since it is fully covered by ice, it's a continent, it's almost a continent, where you can go from one part to another without any problem. What is the importance of these two caps of ice in the Earth, in the north and in the south? Well, the most important effect they has for the human being is that they control the present oceanic circulation, and also they control climatic circulation. So they actually controlling our climate. So the present thermohaline circulation is derived from the production of cold water in the pole, which moves southward and now northward, and they develop a three larger component in the ocean, which are the present characteristic of the circulation in the ocean. The formation of this cold water only occur in very specific places. In the north, they occur in the Labrador Sea and the Greenland and Norwegian Sea. And in the south, they mostly occur in two seas, the Ross Sea and the Weddell Sea. The Weddell Sea is the most important one, since it probably produces about 80% of the total cold water which is produced in the South Pole, in Antarctica. The same for the atmospheric circulation. The production of cold air in the north and in the south produce convection cells, which move around the Earth, and they produce, and they result in the present climate. But this feature, these characteristics, are not permanent in the Earth. They are rather recent features that have been developed in the Earth history at a very recent time. If we look into the result of the